Hello, I'm Chung in Energy Harvesting Laboratory, supervised by Sang Kim in Yonsei University. Let me introduce my recent paper published in Joule. The title of my paper is Gigantic Triboelectric Power Generation, Overcoming Acoustic Energy Barrier using Metal-Liquid Coupling. The long-term implantation of implantable medical devices requires packaging materials with high biocompatibility and mechanical stability. And titanium is an essential packaging materials for such implantable devices and has not been replaced in decades. However, titanium shields radio frequency electromagnetic waves and also ultrasonic waves which cause significant challenges for energy transfer. In our research, we represent the first technology that enhances power transmission characteristics through titanium layer using a novel methods using metal liquid coupling. To achieve it, we introduced a new strategy for titanium penetrating triboelectric energy harvesting. This is the exploded illustration for our device, and this shows the mechanism of the device. As ultrasonic waves progress from soft tissue with a low acoustic impedance to titanium with a high acoustic impedance, incident and refracted wave constructively interact, generating intense pressure on the titanium. Microscopic vibration of the titanium induced by the pressure promotes membrane vibration due to the compressibility difference between the liquid and the airspace. The incompressible fluid in the liquid space mediates the elastic waves from titanium, while the compressible airspace allows for the vibration of the membrane. The ultrasonic waves repeatedly induce the contact separation process, thereby resulting in the formation of current waveform with a frequency of 20 kHz. We demonstrate the synchronized vibration of titanium and membrane using a laser vibrometer, and through our novel design, we could achieve the enhanced voltage output to titanium layer. To understand the physics behind the enhanced outputs generated by the device in comparison to the non-titanium device, we conducted simulation and experimental analysis. From the FEM simulation results, when a 20 kHz ultrasound travels to the non-titanium device, the membrane vibrates in multiple nodes, generating um, antinodes moving up and down simultaneously, which is consistent with our prior research, which is published in Science. By contrast, titanium vibrates in a single mode instead of the multi-modes. The presence of airspace between titanium and the membrane prevents the transmission of elastic waves from titanium to membrane. In contrast, the liquid space mediates the transmission of the vibration of the titanium to the membrane, inducing unimodal oscillation in the membrane. So the vibration mode of the membrane is changed by the liquid titanium coupling. To further illustrate the effect of the vibration mode on the device output, we show the mechanisms that depends on the vibration mode. In the multimodes, both up and down moving antinodes are present, which offsets the electrical potential. This offsetting action results in a reduction of induced currents. Conversely, In the single mode, the antinode is unidirectional and there is no offsetting electrical potential. So, it is apparent that device generates enhanced electrical output when operated in a single mode. Then, we compare the outputs. Compared to the non-titanium device, the device with titanium packaging generated a decreased output when combined with the airspace, while the output increased when combined with the liquid space. We compare the average displacement data obtained from the FEM simulation to the device outputs. The results reveal that the average displacement trend closely follows the device output trends, supporting the correlation between vibration modes and the device outputs. We further investigated the material of the repeat space. As we found out in Figure 2, since the airspace hinders the transmission of elastic waves, a significant role of the liquid space is to suppress the presence of the airspace and thereby efficiently mediate the elastic waves of titanium. Air pockets naturally form between titanium and membrane, particularly in the dynamic states when the membrane vibrates under ultrasonic irradiation. To minimize the air pockets in solid interfaces, it is important to consider the wearability of the liquid space. So, we compare two distinct liquids that are commercially available in medical fields, which is silicone oil and saline water. Low contact angle and high F value, which is calculated from the ideal and measured contact angle, indicate that silicone oil is close to the Wenger state and it is suitable for the liquid space. Since the purpose of this research is to develop acoustic power transfer systems for implantable devices, a standardized setup for the characterization of device output that is similar to the in vivo environment is important. So we propose a tissue mimicking material, and using this environment, we measure outputs over depth and power density over impedance and cap charging performance. We found that the titanium package devices had a 310% power density compared to unpackaged devices, which demonstrate the importance of our technology. And we track the in vivo validation of our device. We track biocompatibility and in vivo long-term durability. And we also conducted Bluetooth operation in a rat model. Since it is an important means in implantable devices, notably, the unpackaged device was difficult to operate the Bluetooth module due to its small size, while the titanium packaged device could operate it despite its complex size, demonstrating the importance of this technology. So thank you very much for your kind attention.